we have arrived to this year finding the surprising fact that 2025 is the square of the sum of all the digits, and at the same time is the sum of all the cubes. So 2025 is the square of the sum of all the digits and the sum of the cubes of all the digits. So the square of the sum and the sum of the cubes of the digits. The idea of this is to prove that in fact there is only one surprise. In fact, for whatever number n, the square of the sum of the first n number is always the same to the sum of the cubes of this number. So this is not just a property of number 9, and this is not just a property of 2025. Actually, whatever number that is the square of the sum of the first numbers is also the sum of the cube number. And the purpose of this video is to show that this is always true. And this is a well-known theorem in mathematics that is called the Nicomachus Theorem. Nicomachus was a Greek mathematician of the 1st century. The proof that I'm going to do is a proof by induction. So let's just remember what is a mathematical induction. So when you are going to prove something using induction on n, so on this number, so what you are going to do is prove that the proposition is true for whatever natural number. And this proof by induction is made using two steps. The first step is to prove that the proposition is true when n equals 1. And then, as a second step, we prove that if we're true for n equal k minus 1, then the proposition will be true also for n equal k. So if the proposition is true for whatever natural number, then it will be true for the next natural number. For example, if this is true for 9, then it will be also true for 10. Some people, instead of using k minus 1 here, use k and then here k plus 1. But it's the same, this is equivalent. So what we're going to prove is if this proposition is true for whatever natural number, it will be also true for the next natural number. So these are the two steps of induction. Prove for the first number, and then to prove that if this proposition were true for whatever number, natural number, will be also true for the next. And obviously, by doing these two steps, we were proving that it's true for whatever number. Because if this is true for n equal 1, then it will be also true for n equal 2. Because in the second step, say that if something is true for one natural number, will be also true for the next one. And also, if this is true for 2, then it will be also true for 3. Because here the second step say that it were true for one natural number, will be also true for the next one. And because we have proved that it's true for n equal 3, then it will be also true for n equal 4. And if it is true for n equal 4, it will be true for n equal 5, etc. So by doing these two steps, we have proved that the proposition is true for whatever natural number. So let's do these two steps, and we have proved that this is true for whatever natural number. And to prove this second property is actually to prove that if this were true for n equal k minus 1, so let's write this for n equal k minus 1. It will be then 1 plus 2 plus etc. until the last number will be k minus 1. So this will be 1 plus 2 plus k minus 1 to the power 2, and this will be equal to 1 cube plus 2 cube, and then the last number will be k minus 1 to the power 3. So actually saying that this proposition is true for n equal k minus 1 is saying that this is true. And saying that it's true for n equal k means that this first side of this equation will be finished in k. Yes, so it will be the same of this plus another number k. So it will be this. And this will be equal, so we are going to prove actually this, 1 cube plus 2 cube plus k minus 1 cube plus another number k to the power 3. So in the second step, what we are going to do is to prove these things. And in this proof, we can use in whatever moment is, because we are assuming that this is true. This is what the second step of induction say. If this were true, then it will be true this. We're going to prove, actually, if this were true, then this will be also true. So let's do these two steps of induction. Let's start with the step number 1. So for it, we need to prove it for n equal 1. And to prove it for n equal 1 is very easy. Yeah? So it means that the last, here in the first side of the equation, the last number is 1. So we finish just at the beginning, 1 squared. So let's type this using the last number as 1. So we finish exactly when we start. We have at the right side 1 squared. And at the other side, we finish in the first term, 1 to the power q. So the last number here will be n equal 1. So this will be the last number. And obviously this is true because 1 squared is 1 and 1 cube is also 1. So to prove that this is true for n equal 1 is very easy. Obviously you can prove also that it's true for n equal 2. For example, for n equal 2, we have that the last number will be 2. So it will be 1 plus 2 to the power 2. So it will be 1 plus 2 to the power 2. 1 plus 2 is 3 to the power 2 is 9. So this is 9. And on the other side, we'll finish here in the second term. 1 cube plus 2 cube. And 1 cube plus 2 cube is also 9, because 1 cube is 1, 2 cube is 2 times 2 times 2, 8. So 8 plus 1 is 9. So this is 2 for n equal 2. And you can prove it for n equal 3, etc. But obviously it will be better if we use this induction and prove it if this were true for until k minus 1, so it will be also true for n equal k. So let's go to the second step immediately. So and then for the second step, so I'm going to prove this. So I'm going to start from the right side and I'm going to finish in the left side. Let's start from here. 1 plus 2 plus etc. plus k minus 1 plus k to the power 2. So let's start from this. And notice that this is actually the sum of two numbers. We can consider this as the sum of two numbers, as the sum of the first k minus 1 digits, the first k minus 1 numbers, plus the last number k. So you can, one way to type this is to type that this is the sum of, I'm going to put in bracket, the first k minus 1 number, plus the last number k. So you can consider whatever sum as the sum of two numbers. And this sum of two numbers is to the power 2. So I'm going to use the very famous binomial square. So you can consider this as a binomial square. So I'm going to use this. Remember the formula of a binomial square. A binomial square, a plus b to the power 2 is the first square plus 2 times the product of the two numbers ab plus the second square. So I'm going to type this the first number square plus 2 times the first number times the second plus the second number square. So the first number's square will be this 1 plus 2 plus until k minus 1 square. So it will be then plus 2 times. So I'm going to write plus 2, and notice that this is 2 times the first number, that is the sum, multiplied by the second, that is k, plus k squared. So balance this k squared plus k squared. And now that we have this, we notice that this first part is what we call the induction hypothesis. So what we are going to consider as true, we are going to consider that for the first k minus 1 natural numbers, this is true. So here what we have is 1 cube plus 2 cube plus k minus 1 to the power 3. So I'm going to type it here. And then they say plus 2, so I'm going to type plus 2. And then we have this term 1 plus 2 plus etc. until k minus 1. But this is the sum of the first k minus 1 numbers. And remember, this is an arithmetic progression. And we know what to do if we have an arithmetic progression. Let's type here the formula for the arithmetic progression. If we have the sum of whatever arithmetic progression will be n, the number of terms on the arithmetic progression, multiplied by the sum of the first numbers plus the last number and divided by 2. So we know here this is an arithmetic progression, so we are going to know n is the total number of elements in the sum, So it will be 1, 2, we have k minus 1 numbers, so it will be 2 multiplied by k minus 1. Multiply by the sum of the first number and the last number. The first number is 1 in this progression. The last number is k minus 1. So it will be 1 plus k minus 1. And 1 plus k minus 1 is k. Everything divided by 2. So divided by 2. And then close the bracket. So this is 2. We have multiplied by this progression, multiplied by this k. So multiply by this k. And then plus k squared. And we notice that here 2 and 2 cancel. So let's do this. 2 and 2 cancel. So we multiply by 2 and divided by 2. So actually what we have is this k multiply this k. This is k squared. And this k squared multiply this binomial. So this k squared multiply this k, that's the answer is k cubed. So let's write this in this way. So the first term is the sum of the first cube, k minus 1 cube, plus this k times k is k squared multiplied by k is k cubed plus k cubed. And this k squared here, multiply this one, it will be minus k squared. So we finish with this and we add this plus k squared. And now what we have is that k squared and minus k squared cancel. So we cancel this. And we have that the square of the sum of the first k numbers, natural numbers, is the same of the cube of those numbers. So we have proved what we wanted. We have proved the second step of induction. And because we have followed the two steps of a mathematical induction, we have proved that for any natural number n, this is true. And with this, I finish this video. I hope you have found it useful. Thank you.